So this video is going to focus on limits at infinity. By definition, it says that if f of x becomes arbitrarily close to a finite number L for every large and positive x, then the limit as x goes to positive infinity of f of x is equal to L. Then we are also told that the line y is equal to L is a horizontal asymptote of f. So we're talking about limits at infinity. So as the limit as x approaches infinity, as the limit approaches negative infinity. So we're going to look at those types of situations. So what we're also going to find as we're finding limits of things that approach infinity, that those limits do also tend to be the horizontal asymptote of the given function. So let's evaluate the following limits. We first have the limit as x approaches negative infinity of 2 plus 10 over x squared. Now, limit laws say that I could break this up to the limit as x approaches negative infinity of 2 plus the limit as x approaches negative infinity of 10 over x squared. Now, rules of limit says when you are taking the limit of a constant, the limit of a constant is just going to be whatever that constant is. So since there is no x for us to plug into, there is no negative infinity, the limit of this is always going to be a 2. That is all we have is a 2. It will always be 2. So we just drop that number down. Plus the limit as x goes to a negative infinity of this rational function. So what we need to remember about limits of rational functions is that if your variable degree is higher than, if your denominator degree is higher than your numerator degree, that means your denominator is going to get much larger so much sooner than your numerator. And if that's the case, um, the larger your denominator is, the smaller that numerator is. It's going to go to 0. So what we should know about this, if we plug in, so think about this, 10 over 10 would equal 1. 10 over 100 would be 0.1. 10 over 1,000, 10 over a million, 10 over a billion. This number is going to get so small, and it's going to get closer and closer to 0. Now we are plugging in negative infinity, so maybe in your brain think about if I plugged in negative 100 million or negative 100 billion into the denominator, what would this look like? Well, we got to keep in mind that we're plugging in for x and x times x, right? We're squaring it. So it doesn't matter if we plug in a positive number or a negative number. When we square it, it's going to be positive. So this is going to be positive heading towards 0. So we can then claim that the limit of this is 0, which means the limit of our whole function, 2 plus 0, is a 2. We can say the limit of this is a 2, which by definition also tells us that we have a horizontal asymptote at y is equal to 2. So let's take a look at another example that's very similar. So we're going to look at as x approaches infinity of 5 plus the limit as x approaches infinity of sine x over the square root of x. So limit laws say that we can do the limit as x approaches infinity of 5 plus the limit as x approaches a positive infinity of sine x over the square root of x. Now, same thing, taking the limit of a constant is going to be what that constant is. So the limit as x approaches infinity of 5 is a 5, plus the limit as x approaches infinity of sine x over the square root of x. Now, this one here is going to be a little bit different. In order to find the limit of this, first taking a look at a numerator, what we should know about the sine function is going to look something like this. And what we know about the sine function is that it oscillates between a positive 1 and a negative 1. So the limit is always going to be between negative 1 and positive 1, but it's going to bounce back and forth, back and forth, back and forth, positive, negative, positive, negative. All right, so that's going to present a problem with us, especially when we're dividing it by the square root of x. So for this function here, in order to find the limit of it, we are actually going to need to use the squeeze theorem. What we're going to do is we're going to do this here. We're going to say that sine x, right, oscillates between a positive 1 and a negative 1. So sine x will then always be less than 1, right? But it's going to be greater than a negative 1. We know sine is between negative 1 and positive 1. So we're making this statement. Now, our function is not just sine x, it's sine x over the square root of x. So if we take each one of these and put them over the square root of x, we can now claim that since sine x over the square root of x is less than this function, but greater than this function, take a look at where these functions would go to. Well, the limit of this function, 1 over the square root of x, again, your degree of your denominator is larger than the degree of your numerator. This is going to go to 0. Same thing here. Our degree of our denominator is larger than our numerator. This is going to go to 0. So if sine x has to be less than or equal to 0 and greater than or equal to 0, it obviously means that sine x has to have the same limit as these two here, right? If sine is in between 1 and -1, and these two have limits of 0, well, it makes sense that what's in between them is also 0. So we can say by the squeeze theorem that the limit as x approaches positive infinity is 0, making the limit equal a 5, which tells us we have a horizontal asymptote at y is equal to a 5.